Okay, Gillian, over to you.
Good morning, everybody, or good whatever it is where you are, and thank you, John, for not only organising this whole series of talks about plumes, but allowing us to speak. And today it is the time of the time of H Natland, who is going to lecture us on Mantle geochemistry and what they have to say about plumes. So I've known Jim for 20 years. It's been a tremendous pleasure that whole time. Jim was a professor at the University of Miami, Florida, and he's now emeritus there and living in the mother of all plumes location of Hawaii. Jim and I have published many papers over the years and tried to highlight the fact, which in our opinion is that mantle geochemistry cannot see plumes. So just following on after Jim's title here. So it was highlighted some years ago that if you ask a seismologist, you know, whether their data requires plumes, they'll say, well, no, my data doesn't require plumes, but geochemists see these plumes, so we know they're there. And if you ask a geochemist if their data requires plumes, they say, no, it doesn't, but we know plumes are there because seismologists see them. So Jim is today going to talk about the geochemistry side of things. Over to you, Jim.
Thank you, Jillian. First of all, thank everybody for letting me speak to this group. It's quite a pleasure to talk to people as far away as you all are, and who probably know much more about rocks than I do. I had a lot of going around in circles about this talk because it started out one way and then it would change, and then something would come up and I would change it again. And I was still changing it as little as half an hour ago. So we'll see how it works out. What I realized when I did this was that there's much more to talk about than I can possibly talk about in a single hour or less. So what I want to say mainly doesn't have so much to do with the details of geochemistry, which gets a little bit arcane, excuse me, but how this fits in with sort of the geology and plate tectonic background of the whole business. And that's where I'm going to take this talk today. I will say something about what got me into it in the first place, which was a consideration of comparison of Iceland to South Africa, Karoo and Deccan, looking at the influence of assimilation of silicic materials from granites and other sources, or differentiation to produce those things on the compositions of volcanic rocks, because I tended to believe that if you are going to talk about the mantle, you really must get rid of all notions that you have something in the crust that's interfering with it. You have to eliminate that possibility. And I couldn't do it. I couldn't get to the point where I was happy that people had seen through all the stuff that's going on in the crust. So that's a little bit about what I'm going to say today. So here is the introductory slide, which has kind of a celebratory picture of a famous South African geologist, after whom a stamp has been issued and a fracture zone at 53 south of South Africa has been named. And I've actually been to that place a long time ago. So let's see how this works. This is my field area. So I am sort of an interloper. I'm from the outside looking in. And there are three colors of dots on this slide, which show the kind of things I've worked on. The clear ones or the white ones are mid-ocean ridge basalts. The green ones are gabbros. If it has an S in it, it means that I've dealt mainly with the sediments of those particular places, and all the rest, the red ones, are some sort of island, seamount, linear island chain, quasi-plume, if you will, places. If you like snow on the fantail and gale force winds, go there in a ship, like the Toy Fracture Zone, or here on the Altanan Fracture Zone off to the right. Can you see my cursor on this, by the way?
It's all good, Jim.
Okay. Anyway, that's my field area. Now, this is, in my view, the largest lip, large igneous province possible. It covers 2/3 of the surface of the Earth. It's the ocean crust. And we'll get to some comparisons of the sizes of lips to the ocean crust in a little bit. Here is Jason Morgan, who's one of the nicest people I've ever met, getting a medal for his work on plate tectonics and mantle plumes. What he did was assume that plumes there's about 20 of them, and they're fixed with respect to each other, and plates pass over them, and there's kind of a blowtorch effect, and linear island chains result. So if you take a look at the bottom there, there's the plume convection coming from the core mantle boundary. He did not draw this diagram and did not say that the things came from the core mantle boundary, but in any case, there's the whole Pacific plate passing over Hawaii and seamounts being produced off to the west. I live on this island right here, Kauai. And so the idea of his, in a way, was to resurrect the two-limb convection model for plate tectonics, well, what became plate tectonics, but it was first proposed by Arthur Holmes to explain continental drift and continents drifting apart. And so this thing right here in the colored slide shows whole mantle convection coming up beneath a spreading ridge and pulling it apart. What he tried to do when this proved somewhat difficult to justify for all ridges was establish that plumes were doing this, and there were concentrations of places along ridges where material is welling up, and this was actually driving plates. The problem is this never explained plate motion, and it never explained the changes in sizes of plates or the fact that spreading ridges move around. And just note the similarity of the hotspot convection model to the spreading ridge model for mantle convection. Now, I'm influenced strongly, I was influenced strongly by Don Anderson, who constantly talked about fallacies. One of them was called the drunk at the lamppost fallacy. And you assume that what you see is all there is. So the place you're looking at directly beneath you, it's like you flash a flashlight down, and that's the material that's doing everything. So in geology, we've had varieties of this kind of point of view. Ocean basins are submerged continental crusts, said Erwin Seuss. All you need to know about the ocean floor can be seen in volcanic islands. That was R.A. Daly, Reginald Daly. All mid-plate volcanoes are like Hawaii. All volcanic chains are like the Hawaiian chain. All of those have this drunk at the lamppost fallacy embedded in them. Now, take a look at the African plate, which is just off to the left on this diagram. Once upon a time, the plate boundary was the African continental margin all the way around. The plate itself has gotten bigger. It's now 2 or 3 times larger, and the plate boundary is the spreading ridge, which is in red around it. And it's moved away from the Antarctic plate, which is assumed fixed in a lot of models. And so what it means is that things like ridge triple junctions, one of which is here in the Indian Ocean, this thing has moved. These things sweep across the ocean floor. They move, they migrate. They do not stay put. And so if you have fixed plumes driving plates, these plates will move away from them. So there's lots of triple junctions. You can see one over here, Galapagos spreading center and the East Pacific rise, the Chile rise, okay? All of these are moving. All of these are dynamic features. So if plumes drive plate motions, do they also migrate? Most people will say, well, they have to if plumes exist, but the question is, do they really exist? And so considering size, a lip, a large igneous province, how large is large? So take the area over here for the Karoo Basin, block it out a little bit, shift it over just straight over here to that spot there. It's about the size of it, and that's how it compares to the spreading ridge, the East Pacific rise, at essentially the place where it's spreading the fastest. So it's all contained within a boundary that's less than 10 million years old on the East Pacific rise. The crust there is on the average 7 kilometers thick, consisting of about a kilometer or a kilometer and a half of basalts plus dikes, and the rest of it is gabbro. If there were that much basalt and gabbro covering southern Africa, I think you'd know it. But I don't think it's there. So lips, the scale of lips is, they're huge things to walk around on land, but they're small potatoes. They're diddly squat compared to spreading ridges. So my perspective has been colored by the fact that we have pretty good maps based on gravity and other things of places on the seafloor. And so this is a chunk of the Central Pacific showing splotches of islands and seamounts. And I've just taken a pencil or a pen to these and colored in where there are ridges. For example, these guys over here are right over here. And these features are generally about, if they're red or orange, they're generally about 2 kilometers above the seafloor. They're invariably capped with enriched basalt or ocean island basalt. Of course, you have to understand that ocean island basalts never erupt underwater, right? Anyway, the experience of 50-odd dredge holes on older crust indicates that these things are all enriched. Did all of these things come from the core mantle boundary as the plate was sweeping overhead? Did they all? So if you go to the far western Pacific, where we have Jurassic ocean crust out there, oops, what happened here? Jurassic ocean crust out here, the belly button of the Pacific plate, the earliest Pacific plates, it's a ridges surrounded this chunk out here, and there are seamounts where all these dots are. Here they are over here on a chart. And there's no obvious, what's going on? Where is it? There. There's no obvious linear island chains in this whole place. Whereas Jason Morgan would have said that all of these features that are called plumes produce linear island chains. There are none out here in the oldest part of the Pacific. All have ocean island basalts, so-called, and scattered ages. Are these recycled pot shots from the core mantle boundary? Now, the order of subsequent presentation here is going to be like this. I'm going to give some preliminary thoughts on plumes, geochemical data then and now, which are kind of brief. Now I want to talk about the influence of silicic melts on basalt compositions, and then the mechanism of Karoo Basin igneous intrusion, which I got into just by reading some of the current literature. Subcontinental lithospheric mantle is also found on the Southwest Indian Ridge. It's been taken out from under Southern Africa and is now present at the Marion Rise. Now, a thought again is ocean island basalt a lava that never, not even once, erupts underwater? It's a misnomer. Anyway, if I were to say how to get into this, all sorts of approaches to be taken based on which thing you want to look at, isotopes or trace elements or geophysics or offshore geology or dikes, sills, minerals, plate tectonics. Which part of the elephant should I study that will tell me the most about what I want to know? And it's a big topic. So my personal perspective on this is threefold quotes. One, the upper mantle is a mess. That's from Marjorie Wilson, who is the editor of Journal Petrology. Nature is a triumph of kinetics over equilibrium. That's from Al Engel at Scripps. Magma mixing is a fundamental process. Mike Rhodes, University of Massachusetts. These three things together mean that assumptions of a homogeneous mantle in experiments and models are wrong. But that's what we have to work with. Compositions of natural basalt classes never fall along a liquid line of descent. They're always mixtures. Picrites also are always mixtures, which means that crystallization and potential temperatures, compositions of parental magmas cannot be inferred from olivine melt or aluminum and olivine geothermometers. All of that is out the window. So there's my picture of the upper mantle. That's the Tohoku earthquake, tsunami debris. And As for plate tectonics, triple junction ridge magnetic patterns are chevron shaped with narrow diking parallel to those anomalies, presumably narrow diking. This is standard ridge crest tectonics. This is Shatsky Rise in the far western Pacific. And after having gone out there and drilled there, I'd say there's nothing but more but Shatsky Rise. It's not an OIB kind of place. And again, triple junctions migrate. In this case, they migrated from down here, up here, to this direction up here, giving you these chevron shapes. Plume hypothesis requires hitting a moving target then, if this is a plume, which might be like skeet shooting from the core mantle boundary. Is that realistic? So this place is about as big as Olympus Mons, which is over here on the right, lower right. These are big volcanoes, big structures. But how they got there and why they're so big is still to be determined. How far can we go with plumes? Hypothetical deep mantle plume on Mars has been speculated about. The origin of the Tharsis region. It's a cartoon, in this case generated by a computer at the University of Virginia. Well, what we really know about mantle convection on Mars is that, okay? What this is telling me is that this is an example of what was once called metaphysical pathos, which is wanting something so desperately to be true that you never give it up. It's there. It's part of your thinking. It's part of the fiber of your being. I encounter people who think I'm killing their children when I say that I don't believe in plumes. Well. Now, then and now, lots of things have happened since I was a kid. We used to have 3 or 4 isotopic systems, used optical properties, indices of refraction. Now we've got about 8 or 9 or 10 isotopic systems to think about. We used to do trace element methods, get maybe by atomic absorption or XRF and get maybe 20 elements. Now we have laser ablation, ICP, plasma mass spectrometry. We measure routinely 69 elements for the periodic table. Then we had a 3-channel electron microprobe. We hand dialed the peaks. We had backgrounds. We punch cards, submitted it overnight, and hope it compiled before we could see the numbers. Now we have 6 to 9 channel automated EPMA classes plus laser ablation for trace elements, backscattered imaging, melt inclusions. You dial it in, you get some sleep, you come back in the morning to a stack of data. Then we have precision, 2 or 3 significant figures, maybe 4 for some isotopes. The accuracy was variable. Now, you got 4 to 7 significant figures, repeatable from lab to lab with uncanny accuracy, and we have it all on a big database, GeoRock. For consequences, we throw out the old data, we rewrite the papers. We need to have a lot of money for the machines and for expertise. We have massive headaches as a result, and we are dependent extremely on isotopes. Nobody looks at thin sections. So, as an example of one of the things that's come on, Rhenium-osmium systematics. This is a diagram that was produced by Alex Halliday for a News and Views article that he wrote about, among others, Laster and Howry's paper on the rhenium-osmium system. So it's the Wilson cycle view of mantle geochemistry, whole mantle convection. What's required is a round trip through the mantle. You take all these low temperature things that interacted with hydrous crust and upper mantle, EM1, EM2, high mu, phoso, C, whatever you want. Up, down it goes all the way down to the core mantle boundary and then back up again. Does that strain credulity? This is an outrageous in a way hypothesis, and it needs a lot of proof before it can be accepted. But that's what people are talking about. So anyway, as for rhenium, I thought I'd better find out what it is actually. So it's a transition metal, atomic number 75, rare in the crust, usually in parts per billion. It's named after the Rhine River. Tends to be associated with sulfides in lavas. It's only been well measured in the last 30 years. Beta decay from osmium 187. Long half-life, 41.6 billion years. Isotopic systematics indicate very old ages in basalts. Most abundant in organic rich sediments like the Black Sea. Why hasn't this been considered in basalt geochemistry? The old surface of the Earth had very little oxygen. Weren't there subducted or recycled sapropels or black shells, which would influence this? What is the age of dust blown from continental cratons? What was it 2 billion years ago? So if you look at Laster and Howard, you see they want to explain the difference between the Kea and the Kilauea and Ko'olau volcanoes on the islands of Hawaii. So there's this isotopic difference, which is expressed in strontium 87, 86, and in the osmium isotopes. And they got some samples of gabbro from some xenoliths that were collected on the island of Hawaii and Hualalai volcano. And they differ from either one of these two mixing end members. The contrast between the Loa and Kea trend is responsible for what's called the zoned plume hypothesis for Hawaii. These guys up here in this paper required pelagic clay in order to get these kind of numbers. They were also dealing with some oxygen isotopes. So over here on the right is their model. Now, what their model showed was subducted, hydrothermally altered ocean crust and upper mantle going down the tubes, back up again, down the tubes. And they were skeptical maybe about going all the way down to the core mantle boundary, but they had it recycling to the 660-kilometer discontinuity and coming back up as some kind of a plume. That's what rhenium-osmium is about. That's what these, the question is, was there a deep mantle plume? And they say, well, maybe, don't know, not for sure. So if you take a look again, how large is, did I already show this? I think I did. If you take the area of the Karoo and you shift it over here and compare it to the East Pacific Rise, it's pretty small. We have mid-ocean ridges, so-called, but then there's some that are not mid-ocean ridges, like the Juan de Fuca Ridge or the Galapagos Spreading Center of the East Pacific Rise coming up into the Gulf of California, or the Carlsberg Ridge off of Africa. So even the term mid-ocean ridge is biasing our thinking about how these things work. So now pelagic clay, which is figured in some geochemical models. It comes from wind-blown dust off of deserts like the Gobi or the Sahara. There's a Pan-African granite signature to dust washed from cars in Miami. And it shows up in the Antilles arc basalts and andesites. It's concentrated in oceans below the carbonate compensation depth, as in the Western Pacific. It's iron rich. It's ubiquitous. It's everywhere in all marine sediments. It's very dilute, but it's some component of it is there, including carbonates. Even the purest carbonates have a magnetic signature. They have some iron. It comes from the wind-blown dust. It usually contains silicious organic dust from dried up lake beds. Darwin found this out first thing out of England when he went on his voyage of the Beagle. It's very oxidized in current oceans the last few 100 million years, and it picks up iron from reaction of particles with seawater. Is it the source of EM1, enriched mantle 1, as Laster and Howry would have said, or other people? There's a very slow accumulation rate in the Southwest Pacific. So I've been there, TSDP site 595. It's 1/3 of a meter per million years, as far from dust sources as possible. All right, so if you want to take a look at it, that's what it looks like. That's a core turned on its side. So the top is on your lower left and the bottom is on your upper left. So this is an almost 9.5 meter core, piston cord, and it's almost uniform clay. No carbonate, no silicious microfossils, below this carbonate compensation depth, only dark red clay and fish debris. Largest iridium anomaly ever seen is at the Cretaceous Tertiary boundary, which is at 17 meters. Only 70 meters altogether at this site. That's 1/3 meter per million years. That's pelagic clay. So then and now. Then in the Karoo, we had georock data set, which looked kind of like that. That's just titanium versus MgO. So There are two sets of rocks. There's a low titanium group in green and a high titanium group in blue. Picorites with a greater than 11% MgO have yellow dots on them. These are basically accumulations of olivine in these kind of rocks. This kind of a trend means you're on a cotectic. You're crystallizing olivine, plagioclase, and clinopyroxene. These guys out here have this as the basis of the ground mass, and they're full of olivine added by some mechanism. Then there are silicious rocks. These are the high silica rocks going down to rhyolite. So all of that was in Karoo in 2005 when I looked at this. Now we have this. This is the kind of range of data available now. It's thousands of analyses, lots more data. No silicic rocks are on this diagram, which chops off an Mg number of about 20. This is from Lou Ashwell's paper of 2021. The stars over here on the right were studied in detail. Many of these analyses are obtained by high precision techniques, and most high titanium analyses are here in the Northwest. So down here in the basin, we have low titanium rocks, and up here we have high titanium rocks. Now, picorites. Same sort of thing with picorites in terms of TiO2 versus MgO. You see, for example, in Podloping Island in Canada, this particular sample is an example, a thin section view of a picorite. It has many different kinds of olivine glomerulus, skeletal olivines, rounded olivines, chewed up olivines, little straight olivines, and they all have, there's a wide variety of compositions. Most of these picorites out here have these kind of ground mass compositions, or if there's glass available, that's what you see. So these are additions of something with a lot of olivine in it to these kind of host materials. If you take something this titanium rich, or this, which is also equivalently iron rich, and you add olivine back to it and get one of these, and you say, oh, it might have a forsterite 91 in it, and you say that that's, back up. That's what you use to do backtrack calculations. You wind up with a potential temperature that's way too high and an MgO content that's way too great. And that's because you've got so much iron in it to begin with, because this is the host. It's a mixed rock. You can't do that. You can't do this kind of backtracking with these kind of rocks. This was discovered by Dave Clegg when he looked at rocks from the Kilauea volcano. And it's true of everything I've looked at from Juan Fernandez Islands to Iceland and Greenland. So the other thing that's happened is, well, Karoo's been added to. So there's now, it's not just the basin anymore. It's got stuff off to the north and stuff in Antarctica. So these are now north and south. So we have to consider all of these places when we worry about Karoo. Now, silicic volcanism, I want to talk about briefly, mainly from Iceland. First of all, here's a notable early paper I think everybody should know about. If you haven't seen it, dig it out. Geology of Ascutney Mountain, Vermont, by Reginald Daly. And he did this for his PhD. It's an early careful, he studied a basalt granite cyanide intrusion. And it's an early careful integration of the role of basaltic magmatism in partial melting and assimilation of continental crust. It happens. Basalt, the bringer of heat, is what how Daly describes the mechanism. Then there's this paper, another one, a notable paper by Lawrence Wager and others in Phil Trans of the Royal Society. Isle of Skye, the Marscoite, zoned magma chamber with granitic material melted up from continental crust or granulite or something, and basaltic magma underneath with producing mixed rocks. A classic hybrid magma produced by basalt rhyolite mixing. Granites are the melted crustal rocks. So that's what I was looking for when I considered Iceland. The other thing to note is that silicic material is present in the ocean crust. You may not see it in the basalts, but you do see it in the gabbros. And we have a 1,500 meter hole, Southwest Indian Ridge 735B, which we've drilled. Silicic veins are about 600 silicic veins are present in the core. It's not very much of the core, but these things would melt out at 1,800 degrees. They're full of hydrous minerals. So if any basalt comes through this, these materials would melt out probably and assimilate back into the rising basaltic magma. We can't avoid this kind of thing. It's always going to happen. Wherever you see a column of ocean crust or continental crust, if these rocks are down there, if there's gabbro intrusions or if there's granulites or if there's granites, partial melting and assimilation will take place. Can't help it. So in Iceland, there are about 5 to 20% of differentiated lavas, andesites, dacites, and rhyolites, depending on the place. Plus, many basalts with high iron and total iron is titanium. So titanium up to 5%, iron, total iron up to iron as FeO up to 14 or 15%. And anhydrous melts are low temperature differentiated liquids from 1100 to 1000 degrees C. That's the red stuff here. Olivine basalts are at 1150 to 1230 degrees C. If this stuff comes up and sees this kind of material on its way up, it cannot help it. It's going to assimilate it. So that was my concern, was whether this was mimicking what people have been interpreting as mantle heterogeneity. So these Pacific Rise shallow melt lands actually contains low temperature melts on this order. So in Iceland, these silicic rocks appear as tuffs, veins, dikes, and composite flows. They tend to be light colored, pinkish, reddish, which is probably one reason why they're mapped in that way on geological maps. And the evidence for intimate intermingling of basalt and silicic material is all over the place in the field and shows up in the form of what are called emulsion rocks, which are hybrids of basalt and rhyolite. So composite basalt rhyolite net vein intrusions at Austerhorn in eastern Iceland. And this is called the emulsion rock from, can't pronounce it, Berufjör Dartendur. This is work of George Walker. So, question is, what does a small percentage of rhyolite mixing do to basalt compositions? So, one of the things it does is if you start with a primitive basalt that looks more like, as in, where's my cursor? There it is. As in here, under the niobium, yttrium, zirconium, yttrium, delta niobium diagram. Delta niobium 0 means it's plume-like over there, according to Godfrey Fidden, and it's morb-like on this side. But you can take 1 or 2 or 5% of silicic material and drive these compositions straight over the line, as in these models down here. Or you can take the rare earths depleted, and you can just add a little bit of rhyolite to them, and they'll flatten them out or enrich them like that. And if you look at Jean-Guy Schilling's diagram, initial diagram for the Reykjanes Ridge, where he did lanthanum samarium versus ytterbium, just looking at rare earths. And this is the trend he saw heading from up the Reykjanes Ridge toward Iceland. So it's becoming more enriched in this direction, according to Schilling. And this was a signal of mantle heterogeneity, as he described it. But if you take this composition of a silicic rock or this composition and mix them in, these are the trends you get. You kick them over, just a few percent of these things, kick them over into enriched compositions. Or you can change isotopes versus the lanthanum samarium ratio. You can have mixing trends over here. You can even see it in individual eruptions. This is the latest eruption. Julian just sent me this paper. So if you take all the data from this eruption, which occurred just last year for 3 months, this is the variation in a single eruption. All right, it's just like this, or like this, or like this. It's there on the southern tip of the Reykjanes Peninsula. So their diagram to illustrate this was Well, you got something down here that's enriched, and you got something up here that's depleted. Depleted gets displaced by the stuff over here, filled up by this into this magma chamber, and so you had a shift from depleted to enriched with time. All right, and this is their summary diagram. It's only a two-dimensional diagram. It does not consider whether any of these things came in from the side. So, as Bradley Myers and Warren Hamilton would say, cross sections are for tourists. That's what this is basically, even though it's a block diagram. So if we apply this, say, to this opening of the Indian Ocean, the tectogene hypothesis of Daly back in 1933 had basalt and downwarp and crustal thinning and megastoping, he called it, as chunks of continental crust and infaulting blocks of rock dropped into the mantle. What it actually amounts to probably is some zone of mantle gets heated up over here in 2 and probably starts to convect, and ocean crust is formed, blocks form, drop down, and this stuff gets incorporated into the oceanic mantle that's forming in the Indian Ocean. And so you have a chunk of India, Africa, and the Seychelles microcontinent right there with this kind of stuff going on in between. So the mechanism of this, and this shows up in the compositions of the basalts. This shows up isotopically and in trace elements. Mechanism is probably by lateral rift propagation, sideways, not vertical ripping. Try tearing a sheet of paper by pulling it apart and then tearing it from one edge, and you'll see the difference. The mantle doesn't break along a vertical fracture, but was within a region that is heated by repeated basaltic intrusion. This is, or has been termed, delamination. And in the case of Karoo, you have this kind of variability of epsilon, neodymium, and strontium isotopes kicking off in this direction. These are assimilation mixing models starting from something that looks like Southwest Indian Ridge, Mid-Ocean Ridge basalts, starting there. You can go down here, produce some compositions, or kick over here. So this is in a paper by Heinen and Rick Carlson and others. And the most depleted rocks look like those of the Southwest Indian Ridge. I'll get back to that right at the end. Now, in mechanism of igneous intrusion, at Hawaii, you have a central caldera at Halemaumau, and you have lateral dike injection along rift zones from some sort of magma reservoir. Lateral blade-like injection of a dike in a zone of what Mike Rand called neutral buoyancy, 2 to 4 kilometers deep. Neutral buoyancy is when the magma density and the formation density, which is full of holes, full of porosity structure, match. Magma can no longer rise vertically; it has to move sideways when that takes place. So years ago, Dale Jackson and Dick Fisk did a study of, they took some models and showed how if you have a cross section like this, it tends to sag. And the greatest potential dilatancy is at that arrow there, right there. This is the zone of maximum likelihood of dike injection laterally from a central conduit like Kilauea. So dikes propagate laterally in the direction of the least principal stress. They center in the region of greatest potential dilatancy, the largest arrows on the previous slide. They focused on the weakest part of the formation, usually where previous dikes are still partly molten. Result is much dike on dike injection, composite dikes with one-way chilling statistics, 1 quench margin per dike. In the extreme, the result is sheeted dikes, and the dikes are keeled, they have bases. So lateral injection is what you see. Dike direction overall is determined by the shape of the injected body, gravitational stresses. And this they modeled by looking at jello molds, which sagged in the middle. They stuck a needle up into it and injected dye from it, and the dikes, red dye propagated down the length of these objects, whatever shape they had, and erupted at the end. So that's the mechanism of dike injection as far as the Fisk and Jackson story went. And they used a lemon jello mold with red dye for dikes. Now, Mike Ryan added to this notion the concept of neutral buoyancy, which said that there's a zone where the magma density and the formation density, which becomes more porous as you go upward in the crust, match, and the magma can no longer move up and out, it has to move sideways. So that's where dikes inject. And a given eruption, this is a series of eruptions through time, pulses of magma occur at the summit, and it inflates downrift, and it kind of blows up, and eventually an eruption takes place like this here, right there, or maybe there, or there. So this region of neutral buoyancy is the zone of concentration of dike injection laterally along these rift systems. Pulsing of the magma pushes against the tip of the dike, which encounters some resistance. This causes local inflation until eruptions occur. So this last eruption on Kilauea, which was just a couple of years ago, broke through a block at Pu'uo, which was active until 2018. It broke through, and the dike pushed its way down to a major eruption, which occurred between May and September of 2018. All right, it's essentially the mechanism that Dale Jackson was talking about. All right, and what you see at Hawaiian volcanoes is rift zones, which are active along their lengths by this very mechanism. This is on Mauna Loa. There's a rift zone up here, and there's a rift zone down here. There's a southwest rift on Kilauea, and then there's a hooking east rift, which goes all the way out, 70 or 80 kilometers out offshore on Puna Ridge. Some Hawaiian rifts on older volcanoes are as much as 200 kilometers long. Where was I? Right. Now the East Pacific Rise has long, straight segments of eruptive centers at axial highs like this one here between Sakaros and Clipperton fracture zones. This is a narrow zone of eruption right on the ridge axis and has positive relief. This one is here north of Clipperton. Okay. The narrow region of positive axial relief is where almost all eruptions occur. So this is a narrow, it's 500 meters to 1,000 meters wide. This is a narrow dike injection zone. It's probably exactly the same as Kilauea and looks something like this in a cutaway view. So there's some kind of zone of lateral dike injection right at the rift axis in what producing sheeted dikes and lava flows. There's another zone where picritic magmas probably collect at the base of the crust and produce a seismically detected melt lens there. And then there's a shallow one in between. There's upward flow, sideways flow, upward flow, sideways flow, upward flow, and eruption. So this is the mechanism of eruption at the East Pacific Rise, and it produces sheeted dikes, which have been observed in exactly one place at Hess Deep in the Eastern Pacific. They're also found in some ophiolites. So all of this crust, all of this with these magnetic anomalies, which are bounded by age on this diagram. So they're out to magnetic crons for out to 180 million years out here. All of this crust was produced by this mechanism, by these mechanisms. And continents have drifted, plates have moved, continents have moved further apart from one another. Collisions have occurred along belts like this. This whole system is dynamic. Everything is in motion. So, but the mechanism of eruption is almost certainly just what I've described. And what this means is if you take a look at a cross section, there's a narrow zone of magma injection at the base of the crust, which used to be, people once thought there was a magma chamber that was 20 kilometers wide out here. Gradually, seismic studies have indicated that there's hardly any melt in these rocks at all. It's just concentrated in a melt lens right at the top, a few hundred meters wide, 50 meters thick. All these are cumulates, and somehow or other, all of that is produced by melt segregating right at the top, right at the base of the sheeted dike sequence and eruptions of lava at the top. So our picture of the mechanism of eruption has been modified considerably over time, over the last 30 or 40 years. And we now have a completely different picture of the role of cumulates, especially in the generation of gabbros and in contrast between the gabbros and the dikes and the volcanic rocks. But all roads lead to this narrow meltland. So whatever is injected down here has to work its way up to the top. Mixing is inevitable. Mixing has to take place. Everything is a mixture. Now what about Karoo? Well, it's different. It has sills and dikes in sediment. This is papers by Rogers and Schwartz in 1911 and by Rogers and Dutoit in 1909, showing map patterns of these outcropping sills in the sediments. And there's hundreds of them. They're all over the place. They fill the entire basin. And cross sections are on this order, that these sills intrude sediments going down a kilometer or so, and there's a pile of lava at the top that's about a half a kilometer thick right over here. Now, this is not 7 kilometers thick. It's not like ocean crust. It's a lot, but it's not that much. This was not an arm of a migrating spreading ridge triple junction. The dike injection zone did not exist at this location. In fact, the dikes are scattered around and look like this. If you just map the dikes in this region, that's what they look like. They're all over the place. There's principal zones of directions, principal directions, but the dikes are all over the place. What is this? What is this? It's not the arm of a triple junction. And some of these intrusive sills are downdropped in the centers. They're cup-shaped. Up to the north, there's a zone of a three-armed zone of dike injections. But this appears to have been there for a very long time. It's not migrating. It's not a standard ridge triple junction. It is not a triple junction. The dike distribution is dispersed. It has both Precambrian and Jurassic dikes. And it's controlled by pre-existing structure between cratons, according to Jourdain et al. Another hypothesis is that there can be dikes coming from major volcanic centers, as in Scotland, so that these long, straight dikes or curving dikes coming out of Mull and Skye and Run occur in Great Britain. The term has been called an allocogen. This is actually a term of Nikolai Shatsky, who is the guy after whom Shatsky Rise in the Pacific was named. Dikes originate at major intrusions and inject laterally. This is also not the Karoo. What is it? Well, in the South China Sea on the margin, the multi-channel seismic exploration, primarily looking for hydrocarbons, has uncovered thick sediments with cup-shaped intrusions at depth, various kinds. They're caused by cuspate sills. And in plan view, they're scattered around like this. They are below a couple thousand meters of sediment now, but probably they formed when there was about 1,400 meters of sediment originally. And at the time, they fed what are hydrothermal plumes, which are these green objects here, here, and here, here, and here, hydrothermal vents on the seafloor. So these things were below the hydrothermal vents, which were on the seafloor. The sill depth below them was about 1,400 meters down. They are between 3/10 and 3.6 kilometers thick, or in diameter, and 64 to 480 meters thick, according to the detailed investigations of the seismologists who looked at these records. So for Karoo, people say that there was some kind of source region down here, sill injection here, and up here, and eruption of basalts on top. So stages of eruption. Come on. For South China Sea, almost the same situation as hypothesized, except that at the time there was some kind of a stagnant slab, wherever it happens to be down there, several hundred kilometers down. There's dehydration and melting going on in this slab, and it's producing magmas which pop up all over the place, producing sills and volcanoes here and there. So widespread sill injection requires multiple nearly simultaneous magma sources derived from the upper mantle above a stagnant slab at a slab graveyard about 660 kilometers down. This is not a plume. So the Karoo is edged by the Cape Fold belts on the southern side. It doesn't catch the arc volcanics, which are actually seen in granitoids, seen in Patagonia over in South America, over here. So Karoo is then actually, in the old geosyncline hypothesis, if there was a fold belt and intrusion of granites and arcs, pretty much what you're seeing is to the left in what used to be called a molasse basin, has abundant, in this case, in North America, it has abundant carboniferous coal, whereas there's lots of coal in the Cape Basin sediments as well. The trench sediments, so-called now, which in the geosynclinal hypothesis were called eugeosynclinal sediments, and they're full of with ophiolites in them. This was a subduction zone over here. Here's an arc. Here's a basin behind it, and this is where these sills, in the Cape Basin at least, intruded. Now, what's really neat about all of this stuff is that off to the southwest, all along the Indian Ocean Ridge, the Southwest Indian Ridge, it's been dredged, and all these green symbols mean that the principal material recovered in the dredge was hydrated, altered serpentinized peridotite. And there are basalts along here, which have been isotopically analyzed, and these match those of the Karoo, similar to Heinen et al. In 2010. This is the Marian Rise, it's over here. This is a body of apparently delaminated, exhumed, lower, let's see, subcontinental lithosphere, which has been detached from beneath South Africa, and it's now down here on this side of the spreading ridge. None of the things along here, the Prince Edward Islands or whatever, Bouvet over here, none of these appear to be produced by plumes. They are related instead to magmatism along the edge of the Marian Rise. So Iceland over here, this inset, is atop a similar rise. There are no plumes here, and there are no plumes here. And that's the main conclusion I have at this point. So with that, I will consider questions. Thank you. Hello.
Thanks, Jim. Lots of stuff to think about, lots of questions to be asked. Who wants to kick off? Jim, do you want to download or unshare your screen, and then we can get everyone up on the screen, including yourself. There we go.
All right.
Okay. Yeah, good stuff.
Good to see you again. I'll bet Steve Haggard has something to say about this.
You want to kick off, Steve? Stephen?
Apparently not.
Okay. Gillian, you've had a whole lot of comments coming up on the screen, and there was also a request from, and apologies for my pronunciation, Alavita, about a paper dealing with the sort of sideway lateral injection of dikes and growth of dikes. So maybe look in your chat box, Jim, and you can, or afterwards you can send me some of those references, and we'll circulate them.
Geocongress, this one says, don't forget the Geocongress. Where's the chat box?
I posted a comment Just flagging up something which also follows on from previous discussions in earlier talks. That there is this story that on Earth we see giant giant radial dike swarms, and people like to quote the Mackenzie dike swarm. And people have some notion that if you have a plume coming up, then you'll get dikes shooting off in all directions from it. But this is ignoring the fact that once magma reaches the surface, the trajectory that goes along, as Jim showed with his jello diagrams, is purely governed by the crustal stress field. It's absolutely nothing to do with the source once the magma is free to flow into the crust. So if you see some curvature to dikes, it doesn't mean that it's come from a point source. It basically means that it's telling you what the extensional crust field directions were in the crust at the time the dike was injected.
Okay, lateral diking. There's a question from Elizaveta. She says, is there a paper to read more about the lateral dike propagation mechanism? Jackson, Fiskin-Jackson, 1972, Philtrans Royal Society A. I don't have any more details on it, but if you like, I can probably post it or send it to you. That's the original paper about lateral dike injections. Dale was out here in Hawaii, and he flew out to the next island beyond Kauai and took pictures of the sheeted dikes exposed in the volcano of Niihau off to the west here. And there's a sheeted dike complex there. It's produced by this mechanism, by the Hawaiian dike injection mechanism.
Okay, if you and Gillian can send us, some of those articles, we'll find a way of putting them in a publicly accessible place or getting them to all the.
I'll send them to you as I get off tonight. I'll send them to you.
Great.
Or maybe
in the morning. Hi, Gillian.
I'd very much like to hear more discussion between Jim and experts on Southern African geology about the similarities and the differences in the geochemistry of Icelandic basalts and Southern African flood basalts.
What I tried to show was there's a similarity to the extent that both places, the basalts have picked up some signature of silicic material produced by partial melting of granite or granitoids or granulites, or possibly differentiates of basalts themselves. That's similar. The basalts that are freest of this, according to the Heinonen et al. Paper, look like pretty much like more are from the Southwest Indian Ridge. To the extent that the Southwest Indian Ridge is not quite the same as the North Atlantic, there will be some isotopic differences for sure. But I can't say exactly what there will be at this point.
Okay, well, Andy Duncan's probably best to answer that. I mean, Andy's got a great database and seen most of the Karoo volcanics, and I think Jeff Howarth, it was on, but I think he's dropped off probably to get back to lectures. But Andy, do you want to have a go?
Well, I'd just like to start by thanking Jim very much for a fascinating talk. But the specific questions asked, I can't answer. I don't recall the data. I've been out of it for too long. But the real crux of things, I think, with what we've heard with these talks and what came out of Lou's paper last year, is those of us who've been arguing against crustal contamination, at least for the low TI basalts, have to go back, re-examine those arguments and see whether they still hold.
Okay.
I think it's going to be potentially very subtle. That the first time I broached these ideas, Jean-Guy Schilling came up to me and said, I can't deal with only 1% or 2% of assimilation. I can't even get it in my models. That's what he said. I think we're a lot better off now in terms of high precision analyses. So we probably can see it more cleanly. But back in the day, he just threw up his hands and was very frustrated with me. But you know, it's 1 or 2% kicks things over from depleted to enriched. That's all. That's all.
Yeah, well, the thing I can say is, I mean, you know, as has been pointed out by a number of people, the isotopic data for low TI Karoo could, I think, unquestionably be explained by crustal contamination. The bit which is still, I think, in some debate is whether the overall composition of the rocks in terms of major and trace elements can be adequately explained. The other problem we have is a quite different one. Large chunks of the Karoo basalts, for instance, most of the pile in Lesotho itself, are incredibly similar in composition. You have the major blocks, which Goodies defined in the stratigraphy, but within those, the composition is amazingly similar. And one of the things which has always fascinated me is if you have a crustal assimilation model, how the hell does it produce such vast amounts of homogeneous or relatively homogeneous magma? I don't query that crustal assimilation can occur, but it's the scale here and the producing really well mixed melts, which I find a little bit challenging to imagine.
There is the same sort of problem, in fact, for the Skaergaard intrusion, which is tens of cubic kilometers of material. People argue for essentially a homogeneous magma entering this magma chamber. And I sort of wonder how this large volume of magma could have been produced and entered a magma chamber without showing any significant signs of differentiation as it did so. I really don't believe that happened. I think it must have been some sort of change, and I think part of it is in the way we evaluate these things, looking at shield margins and what have you. It just, you know, you made a large volume of very differentiated basalt, tens of cubic kilometers at Skaergaard, and it filled up this magma chamber. It filled this whole reservoir up. How did it happen? Where did it come from? Where was that stuff? How did it differentiate to that composition before it got to Skaergaard? And why was it so uniform? But there it is. What can you say?
Martin Clausen, you've looked at lots of Karoo rocks, particularly in the Lubombo. Do you want to comment?
Yeah, I can do that. It's just a very complicated issue, I think. Do you hear me?
Yeah.
Yeah. And it is, you really need to do it more rigorously, quantitatively, to evaluate how similar rocks are, compositions are, how much contamination is required to change the chemical signatures and so forth. So I think it's an ongoing job. I kind of also enjoyed your lateral dike propagation because this is something I've dealt with quite a lot myself. And I've seen some evidence of that on the major scales with the breakup of the continental margins, and quantifying that with thickness distributions. I'm quite, I like that way of dike injections. But then when you get to these giant dike swarms, they are really different. They're really large. And each individual dike is a huge volume. So you're talking about the Skaergaard intrusion being voluminous. It's actually not. If you take one of those dikes, it's a huge amount of volume of magma and so forth.
Right.
So yeah, I could go on with lots of topics that could be brought up, but yeah, those are some of my thoughts.
The lateral dike injection mechanism makes sense when you contrast it to the potential that dikes come up as sheets, as long straight sheets, and come up along a great straight line. I don't see how that's possible. I don't see how stress configurations or stress arrangements will allow that sort of thing. It's like, can you tear a sheet of paper apart by pulling on the edges and break it? It doesn't work. You can't do it. You got to tear it from the edge. It's the same problem. I think lateral dike injection is the way to go.
But I think too, James, I mean, you made the important point of looking at things in 3D, and if you go and look at many Karoo dikes, I think a lot of them were exactly that. They've been injected laterally. Obviously, no break in the crust is or intrusion in the crust is a straight line, as you've also said. And when you do get to localities, you can see the offsets along the dikes. Doesn't mean to say they were not injected laterally, and we see the same in kimberlite dikes. Once you get to the roots of most of our kimberlite pipes in southern Africa, you get these amazing fissure systems, and in many of those fissures you can also see, although they clearly came from great depth because they carry diamonds, you can also see lateral injection, multiple injection, given chill margins and the alignment of sort of crystal mushes on the edges. So I think most of us are in agreement with you. And one thing we must do one day, Martin, is go back to that Olifants River section and sample every single dike, and every single dike that's a multiple dike, and look at that geochemistry sort of dike by dike.
In fact, I've already done that. I've got about 200 samples of the dikes and about 200 samples of the lava flows, which I need to get published up. Yeah.
Okay. So
it's in the process. Yeah. What we see there is kind of like there are some distinct signatures as you go stratigraphically up through that sequence, which are quite interesting. But you also see that recorded in the dikes, because you have a monocline that goes down, means that you go up to higher and higher levels, and that means you're losing the dikes, the feeder dikes, and there's a great correlation between that, and it's kind of illustrated in the paper the structural paper that I give up, but it also corresponds in the chemistry.
No, there's a great story still to come from that section.
Yeah, absolutely. I just need to find the time and the courage to actually get it out. Thanks.
Well, we're waiting for your presentation, so that'll be in 6 months. So you've got a time limit then.
I do have a presentation in 6 months, though, right? Good. No problems. I'll do that.
And you've got GeoCongress in January as well.
Yeah, there is. It has been presented at talks, but it still needs to be published. Yeah.
Okay.
One of the things I've noticed is that the great long dikes that cross from Scotland into England, as far as I can tell, they've only been sampled like once per dike. And there might be an analysis of one analysis per dike, but the long the long dike variation is not known. It's just not known. In the case of Hawaii, that last eruption in 2018, the magma pushed down the rift zone and punched out magma that had been sitting around in that dike, in that rift zone in the crust for 60 years. And the first thing that came out was andesite. Andesite was 57% silica. And that hadn't been seen in Hawaii ever. And what it amounts to is there's mixing between what comes down the pike from the Kilauea Center all the way down these rift systems, and you get a variation in composition from andesite to some primitive basalt composition over time. And that's what these people in Iceland have just discovered in this Icelandic eruption. It takes multiple analyses of individual events before you begin to see some of these processes. And needs to be done somewhere in Karoo.
Yeah. Well, presumably with you living on Hawaii, you sort of, every time there's an eruption, you go and collect a sample with it. So you're looking at everything in a time context as well.
Well, that's the advantage of having eruptions that you can sample as they occur. And the U.S. Geological Survey has dozens of people over there sampling these things. And we're starting to see the results of some of that, like this andesite coming out first in 2018. But my guess is that stuff that punched up from the mantle, which came all the way up the conduit system, probably is only now just reaching the surface. And We don't know what its composition is yet.
Good. Okay, Terence McCarthy, Spike, are you there as well? I mean, I think you had your hand up.
Yep. Just a comment. I was under the impression that conventional wisdom has it that the dike propagates into sigma 1, and that sigma 3 is perpendicular to the dike walls. Because the dike is going to expand, it creates an additional volume. It's going to expand into the minimum principle, the minimum stress direction, and it propagates into the maximum. No, it's not. It's perpendicular to the dike.
The principal stress sigma 1 is straight down. It's gravity.
Well, yeah, okay, but it may be. It could be horizontal. It could be vertical. But the fact is that sigma 3, which is the minimum stress direction, is perpendicular to the dike.
Right.
So, okay, so that it's, in other words, that model that you were talking about earlier is cannot be correct. That sigma 1 is sigma 1 could be vertical or horizontal. Absolutely, we agree on that one. But sigma 3 is perpendicular to the dike. The other thing that I want to make is that the point I want to make is, you know, about this magma homogeneity and so on. My students and I, over a period of several years, did a lot of work on the vertical stratigraphy of the Ventersdorp supergroup. So Ventersdorp, it's supposedly a plume, super plume we've been hearing. And it's bigger than Hawaii. It's bigger than the big island on Hawaii. It's about 2/3 the size of Iceland when you look at the whole province. It's got the Ventersdorp supergroup. It's yeah. And
okay.
Sorry. Anyway, to get on to the point that I want to make is that what we discovered was, well, first of all, let me just explain something to you, which I think is probably unique in the world, is the fact that the majority of the samples were taken from borehole cores, because underlying this supergroup is the Witwatersrand basin. So there's been a huge amount of drilling down to get to the gold-bearing reefs underneath it, and it's up to a maximum thickness of about 1,500 meters of lava, basaltic lava. It's essentially apheric, except for a lower unit, which is the Alberton Formation, which has got large feldspar phenocrysts. What we discovered is that because we've got vertical control on the samples, we've got the XYZ components of every single sample. We've got the vertical position and we've got the horizontal location. And the bars are spread over a distance of several hundred kilometers. What we discovered is that you can divide this magma column into discrete packages of discrete chemistry, and you can trace those packages across the whole of the Ventersdorp supergroup distribution. There are about 9 different packets of lava, each one with a distinctive composition, and every now and then it changes from one magma type to another, but instantly across all of the boreholes. You can draw a line across all of these vertical chemical profiles, and these groups, the groups that are consistent. There's a consistent lateral stratigraphy. So I'm puzzled by how this could actually come about, with what kind of process is going on in the mantle that can rapidly and instantly change the composition of the magma that's being erupted. There's no mixing. There's no evidence of mixing between different types. It's just one type will switch to another type instantaneously. And I think that it's studies like this, which really is, when applied the isotopes and so on. This was done in the old times you were talking about with XRF. So the element suite is limited to about 15, 20 elements. But that there's a huge amount of information that we glean from this, which cannot be obtained anywhere else because we haven't got the 3-dimensional location of all these samples. So I think there's a lot that can be learned. And the other thing about it is we've also got underneath the dikes that fed these lavas, because they've mined out the gold-bearing strata underneath, and the dikes are there to be sampled. We've done some work on this, looking at the stress fields and how they've changed during eruption of the magma, but only on two parts of the Witwatersrand basin, or 2 parts of the Ventersdorp supergroup. So there's lots of opportunity to really look at the anatomy of it in 3 dimensions of a lip, and a substantial lip, a big one.
These are all lava flows?
All lava flows, yeah, absolutely.
Right,
well, the rule was, sorry, just if I can just clarify that. When you're logging the core, you can see you can see individual flows, because the tops of the flows are associated with amygdales and chill zones and so on, and brecciated, sort of R-type lavas. So you can see those. So the students that were assigned to this project were sampling the centers of individual flows. So we've sampled almost every single flow in these lavas in the sequence up to, as I say, up to over 1,000 meters thick. So the quality of the sampling is superb, but we're just lacking in data. Like, for example, we don't have rare earth data. So, so that restricts the thing enormously.
What is the lateral extent? What is the lateral extent of these discontinuities? Kilometers?
Yeah, no, we're looking at 300 kilometers.
Over 300 kilometers.
Yep.
And Spike, aren't you talking about, and more I hear that multiple lips, in fact, in the Ventersdorp?
Well, yes, I know, but this is just the Klippler-Fiersberg group, and then we've still got others that people are proposing as other lips, because we've got on top of that there's the Plotberg, which formed during a sort of basin and range type extension. So there are these grabens which contain a lot of felsic, but also some basaltic volcanics, but they're not widely distributed. And then overlying all of this is the Boerteville, which is a very extensive volcanic province, but not very thick. And then, of course, we've got, yeah?
No, carry on, sorry.
Underneath that, there's the Dominion, which is, people have been, in previous talks, I've spoken about the various lips that are stacked up there. I think Lou, they've got 4, Lou's working on 4 of them. The Karoo's the last one. And then underneath that, we've got some others. But I think there are 5 actually, maybe excluding the Plotberg group. So so we've got that. These are very extensive, but the coverage that we have for the Klippler-Fiersberg lavas is unique because of the gold, the presence of gold underneath it. And
okay, so what are you doing? What are you doing in your second career and in retirement?
No. I'm trying to encourage those guys at WITS. I've been working on Lou Ashwell for years to get him to look at this problem, but he seems to be besotted with this. Where does the lava come? Where does the magma come from? But what this data is potentially telling us is what is going on, the actual mechanical processes that are taking place. So we can look at the dikes, we can look at the lava flows, we can look at how they relate to each other, and I think there's a fantastic story that we can get out of this volcanic assemblage.
And do you have any of your bright young students working on
no, I'm thoroughly retired. I have no students.
You can't run away now, Spike.
Sorry?
You can't run away now.
No. Look, I think it's up to guys like Lou and his team, because Lou's got this team that's working on these lips. And the best lip to focus on is the Ventersdorp, without a shadow of a doubt. And the other thing is that we've collected all these samples over a period of about 5 years. And most of those samples are still lying in the basement at WITS. So it's not a question of going back to the core. And a lot of the data is described in theses or honors projects. So a lot of it's there already. It's just a matter of locating the sample to do all these different types of elements, rare earths and all these isotope systems that we've heard about. But the rocks, one of the problems is the rocks have undergone low green schist metamorphism, and there's been extensive migration of alkaline elements. So things like the strontium 87, 86 is no good. So those systems so you can only work with the large iron lithophile elements, but there are enough of those to really make sense of this wonderful opportunity.
How thick are these lava flows?
They vary, some over 100 meters thick, but it's quite variable. But that sort of stuff is probably recorded in the theses, because the students would describe a lithostratigraphic log and then a sampling log. So we've got the.
As Spike says, it's a wonderful assemblage, Jim, or a wonderful set of rocks. There's some great work done. It needs some new modern additional work or isotopes, but it's a remarkable sequence as well. But it needs and we'll have to speak to Lou about that. It does need some bright young ideas and new thinking as well. I mean, the groundwork is all done. I think Terence has just told us that.
Yeah, look, apart from this additional geochemistry that needs to be done. But there's a paper that you might want to look at. It's by Linton, myself, Linton, McCarthy, and Brown. And it's in the South African Journal of Geology for, I think it's 1994, which describes the opening, well, the way we see the progressive intrusion of these various types of magma, because there's it's almost as if the initial intrusion was done under compression. There was regional compression during which the Witwatersrand deposition took place. But then over the eruption started, and it started dramatically and quickly, because underneath immediately in the layer immediately underneath the lavas is the Ventersdorp contact reef, which is probably the major gold producing reef in the Witwatersrand at the moment. But this reef formed was an erosion surface. It's not a surface where sediments were accumulating by aggradation. It's a surface where material was being degraded. So it's one of the bright young professors, once young, Isaac Rust, referred to this placer as the Pompeii of placers, because it preserves there the characteristics of the reef as it was at the time of eruption. And we've got, because of the geochemical stratigraphy, we can more or less correlate the timing of the eruption, relatively speaking, over the whole basin. But the other interesting thing is that the first lavas to emerge were komatiites. There's this thick sequence of high magnesia basalts up to about 24, 25% MgO. And they form the earliest magma, but that's restricted in its distribution, which you'll see in that paper if you dig it out. And then gradually the extent of the lava flows expand, but the type changes from these high magnesium to a very titanium rich, relatively speaking, not like Karoo titanium rich, up to about 1.1% TiO2. And that's the group that contain these feldspar phenocrysts. So there's this dramatic and instantaneous change from a komatiite to what in terms of the overall stratigraphy is a highly evolved tholite composition. And then from there on, you get a progressive increase in the MgO. So the final eruptives are again running at 18 to 20% MgO. So it starts off with a komatiite, then a highly differentiated, highly fractionated composition, or large degree, small degree, degree of partial melting might change. And then the magma evolves as you go up through the sequence to a high magnesia basalt again. So yeah, there's no weathering at all. You know, if you look at the volcanic, the eruptions in Iceland, you get those red layers which kind of separate the various flow units into these packages. There's nothing like that there. There's no weathering, no indication whatsoever of weathering between these flows. It was simply flow after flow after flow. So it must have been very, very rapidly erupted, the whole package. There is no sediment accumulation except in the very bottom. So yeah, so it's,
okay, that's fascinating stuff, and we await your presentation, or want, an update from some of the young students. And would you send us that article, Spike? And you've got my email, we can distribute it as well. Thanks.
Okay.
How old are these rocks?
2.7 billion.
2,700 million years old.
Oh, crust.
But they're all lying on, the same kind of deep crust that the Karoo is on. It's the same crust. It's a TTG suite of, with again greenstones and so on.
Right.
Okay, I think we need to start wrapping up. Some people have got things to do. Steve Haggerty, have you got any last comments? And maybe Gillian, you can just then give us a 3 or 4 minute wrap up. And I haven't forgotten, we do want to have a follow-up discussion on all the things that we heard, and what we learnt, and what the sort of key points are that should be followed up. And I think, again, Spike McCarthy, thanks for your comments and contributions, Spike. have highlighted yet another, fascinating sequence of rocks, the Ventersdorp, that you've also got to be fitted into this picture, and we need some modern update on them as well. So thanks to everyone for a great series. Thanks to Gillian for originally proposing it and helping put it together. And thanks to all the speakers. Steve, you've got a minute or two if you've got anything to say.
Okay, I just want to thank Jim for a great talk, and also nostalgically, John, I sent you the composite dike materials that we worked on many years ago with George Walker, including the 11-kilometer sequence in eastern Iceland, and the photographs of Bereda Furda was absolutely wonderful. So that's this huge composite dike feeding composite lavas, and yes, there's a lot of acidic material around, including the work that Ian Carmichael did on
Thingmuley.
On Thingmuley. Yes, indeed. Yeah. No. Good. So it was great. Thanks, Jim.
Thank you.
Thanks, Steve. Over to you, Gillian.
Thank you, John, and thank you, everybody. And thank you very much again to OGG for giving us ear on this subject. So we've, over the last few lectures, we've explained why it is that a substantial number of earth scientists strongly doubt the plume model, and these views range from individuals who feel it's completely proved beyond all shadow of doubt that plumes don't exist, to people who are skeptical to various degrees. We've given a couple of examples. I talked about an alternative model for Iceland, because it was pointed out at an early time that it's no use banging on constantly about plumes not existing. You have to explain what the alternative is. And so I gave the example of Iceland, and we had a very interesting talk on Kundo a while ago. I then talked about tomography, and Jim has talked about geochemistry, because these are the primary subjects which are brought to bear on the question. And I've also mentioned that I think this to some extent is a mistake, because as Jim and I have explained, neither method is really very powerful at deciding whether or not plumes exist, because simply neither of them can see deep. That's basically what's going on. Seismic tomography can see big things, and geochemistry and petrology is very good at telling us how old things are, but neither really has the power to see down into the deep lower mantle. I think it's been absolutely fantastic, the amount of discussion that's gone on. I've found that really exciting. And it's also kind of come across most strongly to me is that really this whole series has flagged up so many things that we haven't yet done, and just crying out to be done, because going back to Jim's example of the drunk under the lamppost, we've probably been looking in places, or at least applying tools that we have, rather than being driven by the problem at hand. Or to quote a colleague of ours, if you've got a hammer, everything looks like a nail. So I think I should shut up there, because I'm sure everybody's sick of the sound of my voice. And Mr. Natland, I shall be contacting you very shortly with a view to twisting your elbow to meet up at the forthcoming GeoCongress.
Okay, great stuff, Gillian. Very, very balanced and very tactfully presented. I'm impressed, and thanks to everyone. And I must say, as Gillian said, I mean the points that we still haven't got to, there's another generation's work there to follow. Spike has just highlighted that as well. The Ventersdorp alone will keep people busy for years to come. But for me, it's also been fascinating. The quality of presentations has been wonderful, and the people and the experiences they've shared so openly is also fantastic, particularly so for some of the younger students and us mature citizens, you know, you realize that in this game or this profession of ours, you keep learning every day. So thanks, Gillian. All of the presentations, I think, or other than the one today, are already on YouTube. If you want to go and, you know, watch them in quiet time from the benefit of your desk or lounge, that they're all there. And this presentation will also be shortly uploaded to YouTube as well. So we will keep in touch. I will come back to everyone with a suggested sort of follow-up discussion date. We need to obviously think ahead about a few more presentations from people like Martin, and certainly need some more on the Fences door. So yeah, watch the space, and we in the OGG, Henny and I, and obviously others, really do appreciate the fact that, you know, people have been involved and so open in the discussion as well. Thanks very much, and enjoy the rest of your night or day.
Morning. Thank you.
Morning, sorry. Okay. Thanks, everyone.
Thanks all. Very good series.
Thank you. Thank you.
Thanks, Craig.